1 or plus 1 by subtracting or adding a Cooper pair from the condensate. So that's the hand-waving way why we got rid of the shorts in the superconductor. So now let me show you how this actually works in a toy model. So this is a famous Kitary 1D toy model. So it's a 1D chain of spinless superconducting pairs. So we have sites here, very simple Hamiltonian, some chemical potentials, some nearest neighbor hopping, and some pairing. So pairing is just to nearest neighbors. So I to I plus 1. There's no spin in this, so it has to be p away, right? And you can see that actually changing sign, going this way is plus, going this way is minus. Okay, so we have that Hamiltonian, just repeat it here. Now we change the basis. So we go into a Majorana basis. You're free to do this basis change. It's an allowed change of basis. So you express the C operator as two Majorana fermions, gamma B and gamma A. They satisfy this relation, so they're clearly fermionic. You do this, it's quite easy to work out the algebra, but you get a Hamiltonian look like this. So now you have, each site is now two sites, A and B, like this. So now we just have to look at this. So let's look at two, it's relatively simple, but let's make it even more simple. So again, repeat it here, and then let's look at these conditions. So to put delta and t equal to 0, and gamma is, sorry, mu less than 0. So the only thing that's left is this term. These ones are just disappear. If you just have this term, you see that they pair up. So the B and the A on the same side pair up. So I can draw a little line like this. This is a unique ground state. It turns out there's a vacuum state for the electrons, and it has a bulk gap. You fill it up, and then it costs an energy mu to excite. So this turns out, you can calculate the topological number and so on, but this is the trivial phase. There's nothing particularly interesting happen. Then I can choose these values. So instead now I put this term to 0, and I let delta and t be the same. So this term drops out, and left is only this term here in the middle. Now you see they pair one off. So B on I pairs on A on I plus 1. So you pair like this. So now you can create new electronic operators that take into account what the Hamiltonian looks like, and you define D, and you define a particle. You find an electron D, and if you do this and put this one in there, you end up with a Hamiltonian. It looks extremely simple in new electronic coordinates. This is Hamiltonian has a bulk gap T, but wait a second, we missed this one and this one. This one you can, again, form an electronic operator for, so describe it as an electron. But note that this one sits in one end, and this one sits in one end. So this is one electron with half weight here and half weight here. So this is your half electron sitting on each side of the wire. And this one has energy 0. It doesn't show up in the Hamiltonian. So it's a particle sitting in 0 energy. It's half an electron here, half an electron here. It's clear Majorana fermion because we went into this Majorana basis to find it. And it's also a degenerate ground state because you can either populate this state with one electron, or you cannot populate with one electron, and both of them cost 0 energy, so you don't know which one you have. And that sort of gives you a flavor of the non-locality. So this Kitary model is very important well, it's the first model really showing how you get these three Majorana fermions in 1D system. So what we want to do effectively, emulate this in Weyl materials. How can we find this in Weyl materials? And the question then is, of course, how do we get this half electrons in a real formalism where we have spins and so on? So effectively, the question is, how can I get this half electron in the Majorana fermion in the BGG formalism that we went through? And the thing is, you can never get it if you can express your system in the simple 2x2 BGG formalism, because each degree of freedom here is just one electron. So there will not be Majorana fermions, or free Majorana fermions in this model. So for example, the chiral P plus IP and D plus ID superconductors does not, they have chiral edge states, but the edge states are not Majorana fermions. They are full electronic degrees of freedoms in them. What you need to do is you need to go to this 4x4, the general formalism, and you have to be able, you have to write your Hamiltonian in this 4x4 way, and it cannot be reduced to blocks or 2x2. Because if so, then you're forced to represent one electron by actually two vector components. So you actually double your degrees of freedom here. Remember, we talked about it here. You have a spin up particle represented both by this annihilation operator and by this creation operator. So you kind of artificially double your degree of freedom. That means that each electron is described by two vector components in the formalism. So that means that if you actually find states here, a single state that doesn't have an overlap with other states, then that would be a Majorana fermion that's separated in space. Of course, if you take one of these systems and solve it in a 4x4 formalism, your eigenstates are all coming in the energy of 2. So it means 2 Majoranas gives you 1 electron state, and then you, well, you solve your problem, but you haven't found a free Majorana fermion. So to find superconductors for Majorana fermions, you have to work with this 4x4. And what is the criteria? Well, the criteria essentially is, for example, having spin-orbit coupling, because spin-orbit coupling would couple the spin up and the spin down in the normal part of the Hamiltonian. So that means that you cannot go and describe this term in just this simple way, saying, well, it's just this one and this one. But you also have a mixing between up and down in the normal state. So that's a prototype example of where you have to use this 4x4 formalism. And as I say, just because you have to use a 4x4 BGG formulas doesn't mean you're going to find Majorana, but it's a necessary criterion to find them. Okay, so now I said more technically why they show up in the frame, so in the methodology. Let's look actually how you would do this in real material finally. The prototype example is using a spin-orbit coupled semiconductor, and you add magnetic field. So you start with a semiconductor with spin degenerate, very simple parabolic dispersion. You add spin-orbit coupling, in this case a Rashba spin-orbit coupling that splits this parabolic dispersion into two, it separates them like this. Then you add a magnetic field in the C direction, and that's going to split this degeneracy here. So you get something that looks like this. And now all of a sudden, if your Fermi level is here, your system looks spinless. Yes, so there is spin up here and spin down here, but there's no spin degeneracy left in your problem. We got rid of that pesky spin degeneracy that doesn't allow us to have the Majorana fermion. So now, if you are in this case and you pair electrons here and here, and the good thing is you can pair with conventional S-wave pairing, because these ones point up and this one point down. It's the pairing you need in your S-wave spin singlet pairing. So you can take this spin-orbit coupled semiconductor with magnetic field and just add conventional S-wave superconductor, and you will actually get something that looks like a spinless P plus IP. The only criteria in this toy model here, or I'd say it's not a toy model, but sort of a simple model, is that the magnetic field you add needs to be bigger than order parameter. This splitting here needs to be bigger than the pairing you end up having here. But if you have that, you are going to be in a spinless P plus IP regime that actually is also a topological state.
Could you give me a physical sense of what type of field you need to get this splitting? Is it megatesla? Is it?
No. Actually, maybe this one shows you. Yeah. So, well, if you believe these results, it's less than a Tesla. Oh. Yeah. Yeah. So now let's go and hunt for these in real materials. The first example came out 2012. They used an indium antimony nanowires, a semiconductor with reasonably strong spin-orbit coupling. They put it on an S-wave superconductor, I don't know, maybe it was aluminum or something, and they added a magnetic field in this direction. And the important thing for the 1D system is the magnetic field is not in the same direction and affects the spin-orbit coupling in the wire. So the spin-orbit coupling in this case is this way, magnetic field this way. And the question is then, theory tells you that you should have Majorana fermions here if the magnetic field is big enough. So this is what they initially measured. So this is conductance through the wire going up in magnetic field. And for low magnetic fields, there's nothing at 0, but then looks like there's a peak developing here. The Majorana sits at 0 energy. It should really give you some signature in conductance at 0 energy. Plotting it in color scales, functional magnetic field, there's something that pops up here. Doesn't exist at 0 magnetic field because then you're not topological, but pops up here. So the question is this Majorana? Yes, maybe it is a Majorana. There's one problem here. There's not really a gap here, right? I mean, there's no hard gap here. You start with an S-wave superconductor, you don't really see it here. Things got a little bit clearer, or have gotten clearer since then. This is one example. People have worked a lot on trying to get the superconductor to induce more superconductivity in the wire, to get the coupling between the wire and the superconductor better. So they actually took the nanowire and put aluminum around it. Then you get very good proximity effect into the wire. So this is some results out from Copenhagen, looking at the wire, and the result that they found. I don't want to go into this in detail, but at low, let's see, so here is in a doping regime where it looks like, well, you get a state at 0 energy, and we're going to turn up the magnetic field, but then they split up. So the interpretation here that these are some Andreev states that just cross each other, they are not topologically protected, whereas in the topological phase, they really should stick to 0 here, and this could be the Majorana mode, Majorana fermion, which we are seeing here, because it really sticks to 0.
A question, I apologize, I don't remember the critical field of aluminum. 1 Tesla strikes me as a high field for aluminum. Does anyone remember HC for aluminum?
I think it helps that it's 2D. The superconductor is 2D. It's effectively just a shell.
So you're saying but it's still, if it's granular aluminum, it might go type 2, but generally aluminum's type 1, so it has a low critical field. So I'm just worried about field scales.
Yeah, I'm not the right person to answer. Does anyone know?
Aluminum in thin films is always diffusive. It's type 2.
It's type 2. Do you remember what HC2 is?
The field is parallel, so you need it's like the layer of the aluminum is like 7 nanometers. So there is no.
I see. So it's HC3.
Yes.
But do you remember what it is? Tesla is still a large number.
Well, here you see the gap is closing at 2 Tesla.
Oh, so that's the superconducting gap closing.
Yes, this is the DV, the gap is closing at 2 Tesla.
All right, thank you.
Yeah, so it's a good point. The window here for having superconductivity and still enough magnetic field to be in a topological phase is not an untrivial condition to fit. And in fact, the spin-orbit coupling is good in this case, because if you take your spin singlet superconductor and you apply a Zeeman field, you will actually effectively kill superconductivity just when you reach a topological phase transition. The spin-orbit coupling will cant your moments out of plane and make superconductivity survive this magnetic field, but still the window is not huge. Okay, so this was nanowires. There's also been some data looking at magnetic impurities. So what you do here is you take a superconductor that has either intrinsic strong spin-orbit coupling, or it ends up being a spin-orbit coupling because it's a surface, it breaks inversion symmetry, and then you add magnetic atoms to it. So the first example was using lead substrate and iron, add atoms on it. And then this would become a system where you can use an STM tip-on. So this was the first data coming out of Princeton, and scanning through with energy, and at 0 energy there was a state sitting at the end of the wire here. Here we see it here, whereas the sample taken in the middle of the wire had nothing particularly happen at 0. There are states sitting there and here, and those would be what's called U-Shiba-Rusinov states, or Shiba states for short, that we heard a little bit about on Monday, I believe. So there are other states around, but it looks like there's something sitting there at 0. Just in the last 5 minutes, give you a feeling for a little bit what we do or have done with this sort of system is that we have said, well, actually, this system is pretty easy to model. What we have is we have a superconductor that has some kinetic energy. We can put it on a lattice even and just have nearest neighbor hopping, some chemical potential. We add a spin-orbit coupling to them, and we add superconductivity. And we can solve self-consistent for this order parameter. We just assume it's been singlet S-wide. That's the only thing we assume, and then we calculate the symmetries. And then we add magnetic atoms somewhere. We can add them as a wire or as an island. We just say they can point in whatever direction you want, but you get topology if they find a non-trivial topology if they point out of plane. So if you do this, you can look at single impurities, you can look at wires, and if the right regime you find Majoranas in the endpoints. You can look at vortices in a 2D island. It turns out that you also get circulating currents in this system. This is supposed to be this black thing. I don't have time